Now, when we implement a prognostics and health management system, there are some performance attribute, physical attributes that we have to see, because they are very important, not only from design point of view, but they are important from operation point of view also. So, in this lecture, that is week 4, lecture 5, we will see sensor system attributes and prognostics. What is their relationship? It should form part of our specification, because we want a reliable and safe system for operation, so that it does its intended purpose, and if any failure happens, my PHM should be able to give a advance information about the incipient failure, and I should be able to take the correct mechanism. So, we in this lecture will cover major attributes of the system. So, like there is a performance matrix. I think this has been discussed. We will see the connection of this now also. Accuracy was there, resolution was there in that diagram. So, that was a performance matrix. What kind of performance you expect, and what are the matrix component, which are all are not important, but some of them they will be important, and some of them we can retain for the purpose of uncertainty and all, but all will not, because system becomes very complicated and expensive also. So, if I am meeting my safety requirement by considering 2 or 3 performance measure, it is sufficient. We will see this discussion. Quantification of measure matrix. Let us say, because of paucity of the time, I will demonstrate on accuracy matrix, and one more parameter I have taken, how we can estimate, because unless until I do some testing, I collect some data from the plant, I will not be able to say how accurate my system is. So, that quantification will do. Desired attributes of sensor system and smart sensor. Now, we are into era of smart sensor. So, you can say performance matrix here, accuracy, precision. In fact, I am revisiting the same diagram which I have shown earlier actually. So, sensor application attribute. Now, the thing is, I am preparing a specification, that is the context, and which one I should have it. So, accuracy, precision, resolution, linearity is very important thing. My range should be, whatever my instrument range is there, or requirement range is there, the characteristic of the sensor should be linear. Availability, because I have to take my system, how long it was available. If it is safety system, I should have a maintainability also. If I provide a system which is not maintainable, or which does not allow the maintenance activities to be done, either due to space constraint, or for the the location point of view, or from the point of view of the electronic module itself. So, maintainability should be good, reliability, time constant, uncertainty, and repeatability, and of course, range. So, these are the attributes. I am declaring that accuracy is the closest to the true value. Now, how we do that thing? So, we have a accuracy matrix or confusion matrix here. So, here we are trying to define 3 parameters, not 1 or 2. It is accuracy, sensitivity, and precision. Now, how the matrix are made, the confusion matrix is done. Let us understand first that. You might consider some value as a true value, okay, of parameter or anything. So, if I know the true value of the parameter, okay, now I am seeing measured value, okay, like water boils at 100 degrees centigrade, I know it is a true value. I want to monitor temperature. Now, my instrument value is coming something. So, there should be some relation between these two, okay, close, not close, good, bad. So, we are talking about positive and negative, these 2 terms actually, So, how confusion matrix works? True positive. True positive means the true value and measured value they are in agreement. Okay, so it is a true positive reason. Just for the understanding purpose, I will take diagonal element. True negative. You might say that my true value was wrong, and then it was shown wrong. You know, in English or Hindi we use this phrase. If somebody is negative, you should have some provisions. So if they are having, so true negative. So these two are, my measurement is correct. That means my true value was equal to a positive value, that is true value. So but if true value was not correct and my measurement also shows true value is not correct, then also it is a positive thing. It is showing me the right way, you know. Okay, so these two are clear now. So these are the correct. So I am writing true positive, correct measurement. True value and measured value have positive class measurement. Okay. Second, true negative. That means correct. This is also correct measurement. Negative true. This value was also not correct, and the measured value was also not correct. So that is also, it is telling me the fact. Let us say. So they are true negative. These two we have had definition. False positive. Incorrect measured value. True value is measured as incorrect value. That is not correct, no? True value is measured as false positive. True value was measured as incorrect value. That is not correct. And at the same time, false negative. True value is measured as incorrect value. True value, false negative, no? False negative. True value, which was positive, measured as a negative, incorrect value. So these two should be no. This should be yes. Now, how we define accuracy? How far we were close to the correct measurement? So TP plus TN, addition of these two, and the total number of measurements were TP, TN, FP, FN. All the four sector. Total number of measurements. In linguistic, it converts number of correct measurements. I think it is a pretty elegant definition of accuracy, you know. Sensitivity is TP, that is positive correct value, divided by the actual value, TP plus FN. TP plus FN. This domain was there, which was correct, and I found in TP. So sensitivity was there for the correct decision. Okay. A precision is TP, that means this parameter. Both are correct, measured also correct, these were correct, divided by TP plus FP. Okay, so now precision, TP is again our correct value, true value is this one, and what we got is TP plus FP, okay, positive, negative. Okay, so I think now we are pretty clear about what we mean by definition is one thing, but now visualization through confusion matrix. Now sensor system desired attributes, we have said what are the attributes that we desire on the, see, we want sensor system to be independent because sometimes sensors are located in remote location. Now how about having onboard institutive power management? That means if power supply is cut off, they should operate on their own. Automatic diagnostics, if something has gone wrong, they should be able to diagnose that problem and communicate to the main station. And short signal injection test module, that means that should happen by injection of the this thing, and then it will see at the output whether things are wrong, is correct. If it is correct, module is operating correctly. If it is not, and like this can be 1 cycle per second diagnostic can be done, the way we did for our channels also. Enhanced feature for higher capacity, multiple sensors. Like temperature and vibration, we use extensively in electronics. So there should be provision for 4 to 5 sensors to be connected. Then it will be more useful for us. And IC based sensor, because the size of the sensor should be reduced to the extent possible that we have an onboard sensor only. Then like next, environmental sensor and feedback and maintenance management sensor. So this will safeguard me for any remote cause of failure and common cause failure altogether, whether I am appropriate. This I will clear sensor attributes again, sensor, transducer, whatever multiplexing. This is what we mean by our data acquisition system. Okay, and then we have desirable attribute, which is physical and functional attribute. The physical attributes are sensor category, size, shape, weight, packaging and all. We know that it is by name itself physical attribute. Mounting constraint, some cases the constraint posed by the instrument rack, especially if it is a operating plant and we want to add on to the system, the space we have to create. So there should not be any constraint because of that. Governing criteria, in some location the size becomes the governing. So whenever we upgrade, we have to make arrangement for them, and there should be a planned policy. It is always desirable that the integrated system that facility can provide more parameters should be selection criteria. I mean, as a policy decision, when I am doing a procurement, I will buy with extra channel my sensors, even if it means a little bit extra cost. Okay, or maintenance features. My maintenance team should be upgraded to take care of PHM. So policy decision is a very important thing. And old system, yes, we have many constraints, but we have to do the procurement in such a manner that our purpose is met actually. Or even if it is compromised little bit, it should not be of high significance, it should be of lowest significance. So, keeping in view the previous 3 slides discussion on board sensor, power management and so many other things, we have these sensor systems. It is called integrated sensor system, in which even though I have shown here as a separate module, actually because of this consideration, if I extend this chip size, it will come well within the chip itself. So sensor is on board, transducer is on board, and then ADC multiplexing, and then the output, multiple output will go out, and this will go to end application. So you see all the modules we have built onto one chip, and then not only that, diagnostics also it should perform the way we have said. So these are type of sensors, they are called integrated sensors. Okay, role of process. This is one special topic that I am now discussing in this slide. Okay, I'll talk like it is got huge potential. That means any plant built to manage the system or operate a system, it has got process systems and safety systems, and these systems, they have their own sensors. What we do in PHM, we target an equipment on which, let's say, bearing. In electronics, we might target a capacitor. Okay, but here the process signals are all pressure, temperature, and all those process signals are there. Power. Can I use them as a PHM? And this is area remaining untapped. It will give huge advantages, and I'll show you one example also. Traditional PHM has already technology design, so the system component base. But if I can tap the potential of process system signal which are already available for PHM, there will be huge gain and it will be very effective. So this is, in fact, you can say one more R&D topic that we have launched from this platform. So providing an early warning in some instances, like PHM component basic sensor, they give information about. There are some information that are available in process system sensors, like flow of the system. Like let's say I have a pump which is operating, okay, and it is giving some flow, and that flow is steady state. Now I find that there is a flow drop at some point of time in the day, and I find that this flow is dropping because of reduction in grid voltage, let us say, and that is translating into various electrical levels actually. So the drop in voltage is reflecting into my flow, and there I can see how close I am from the trip value, okay, and I can use this information in our system for prognosis. Okay, the pump may fail, and that is what we don't want actually. We don't want component to PHM. The main objective is we don't want our component to fail or to trip or shut down. Okay, so we got an early signal. I can have management thing in my place. Either I safely shut down the system, or I have some additional capacity to run the plant. Isn't it beautiful way of tapping the available signals? The second advantage is, if I change policy suddenly to PHM for equipment specific monitoring, I will have so many R&D and experience for implementing that. But if I can preempt myself by having R&D experience on through process system, I have built my first thing. So here I am telling this can be implemented, like providing an early warning in some instances by correlating with the PHM and other sensor. This will give a reference information, okay, number one, and providing additional information to supplement or complement the PHM input component. It is so valuable. Either it gives some information before or some additional information later on to the main PHM system, or playing critical part of corrective action and decision management. In fact, information is required even decision making phase also. So these sensors, they can play a lot of role, and health management of not only at component level, but for larger safety and reliability interest of the plant. So the takeaway is, complex engineering systems have process and safety parameters provided needed information to support the plant. This is a normal condition. The potential of this information can be used for PHM as a strategy for maintenance management. So yeah, it is for all of you who are hearing the lecture, how it can be implemented, especially if you are connected with a complex system, it will be helpful. I am just giving one simple example. We have one air inlet, there is a filtration system, particle filtration system in a plant, and the air inlet from the air coming from the plant, and it is being filtered out, and it is put to one pressure filter. This is a filter, though I have not some, I should have, this is a filter element, So the pressure at the before the filter and pressure after the filter will give me information about delta P. Delta P across the, delta P means pressure drop across the filter, and that is an indication of health of the or performance of this filter. Okay. Now I have to, because once the filter start choking, I have to replace it. Now when I have to replace it, that is a big question. How much time is available with me? If I can get this information based in terms of remaining useful life because of delta P information. See, delta P normal, if it remains up to this range, it is normal. But if it goes beyond this, it is increasing like any degradation mechanism. Delta P is we are using as a part of indicator of degradation or lowering of efficiency. So, and here it is upper limit. So that means before this, how much time is available, if I can make a PHM module, you see, I have used the already available sensors, and through these sensors, I am now giving time, remaining useful time or remaining useful life of the filter, and I can have my management in maintenance management in place. And this is what the information I have given. Delta P is the pressure difference across this thing and all. So this job I have done. Probably all of you, it is self-explaining type of thing. This is the control room recorder, it is recording it. Now when my PHM comes, what I will do is, I will tell at any point on this life how much time is remaining. So my operator in control room, he will know how much time is, can I take in this shutdown, can I go to the next shutdown, can I shift it for one day because tomorrow something has to be done, so can I go day after. So many tools. So process system signal as part of PHM is has got a huge scope. That's what I feel personally. R&D has to be done. As I mentioned, in PHM, R&D is part and parcel of life. So now if you conclude week 4, We have studied sensors and data acquisition system in PHM. First presentation was introduction. Second was sensor types and its application in PHM. Third, we focus exclusively on data acquisition system and sensor system for PHM of electronics. That was one part. Now, what and significance of common cause failure in this system. Then system attributes and prognostic. This was 1 week actually, and we also discussed small integrated signal. What I am takeaway for you is significance of common cause failure and potential role of process parameters to tape it for PHM. Okay, so with this end of this 4th week, and next week we will be studying physics of failure. You know, little bit we have been discussing it here and there, but now the module dedicated next week we will have it in week 5, I guess, physics of failure module. Yeah, so one more thing, I have taken from this book, I have given the reference pet and this thing. If collectively you want to see standard format for performance requirement, you can see all performance attribute have come here, requirement for functional attribute. This is a ready-made thing available from this book written by Professor Pett and Dr. Kang, you know, and this can give you a really good guideline to evaluate your sensors. This forms appendix, it is not part of this presentation actually.